Hello to everybody. First of all, I would like to thank PerkinElmer for the invitation to give this webinar about some of our latest research. For those working in ICPMS, carbon is an odd element. You can find information about its polyatomics in the list of spectral interferences, but it's an element usually missed in the ICPMS periodic tables. In fact, it is included in the outsiders group, here in blank, along with the noble gases hydrogen, nitrogen, oxygen, and fluorine. There are good reasons for that. First of all, its ionization potential is only a bit lower than that of argon, 11.26 electron volts. This means that under standard plasma conditions, carbon is ionized in the plasma just about 5%, which affects directly to its performance and detection limits. In fact, carbon detection limits are a bit high for ICPMS, around 1 mg per liter. These high detection limits are firstly due to the low sensitivity of the element because of its low ionization. With our instrument, we are getting around 1000 counts per second per ppm for carbon-13. By using carbon-12, with an abundance of almost 99%, we can get a sensitivity 100 times higher, but we are going to see that this is not a great advantage when measuring carbon. This is because the background levels of carbon are also pretty high as 100,000 counts per second for carbon-13 and 10 million for carbon-12 in water. This background level and its associated standard deviation are the second reason why the detection limits for carbon are so high. The problem with carbon is that it is an ubiquitous element. It is present in air as carbon dioxide, which is also soluble in water. Moreover, carbon is also found in argon as carbon monoxide, carbon dioxide, and different hydrocarbons. We might use higher purity argon or even purge the samples with an inert gas to remove carbon dioxide. But in the end, we are not going to get relevant improvements in relation with the detection of smaller carbon-containing particles. This is because of the cubic dependence of their diameters with respect to the signal intensity. Well, once we know the limitation for the determination of carbon by ICPMS, it's time to make the best of what we have. First of all, we need standards. A number of different compounds have been used as carbon standards in atomic spectrometry, including potassium hydrogen phthalate, citric acid, and oxalic acid. In our case, we got good results with tartaric acid, which is commercially available in 0.2% nitric acid solutions. Next, we need particle size standards. Polystyrene particles are available from a number of manufacturers, covering sizes in the nanometer and micrometer ranges. Although we can detect metal nanoparticles down to around 10 nanometers by single particle ICPMS, this is not going to be the case with carbon-containing particles, as you may guess from the limitation we have just been talking about. In our case, we use polystyrene microspheres in the range of 1 to 5 micrometers. The next issue is the introduction of particles in the ICP. Nanoparticles, which are particles between 1 and 100 nanometers, are nebulized in a similar way than dissolved species. When we use a conventional nebulization system, for instance, a cyclonic spray chamber with a concentric nebulizer, we can get nebulization efficiencies up to around 5%. However, in the same conditions, bigger particles in the range of micrometers are nebulized below 0.1%. To avoid this problem, we have used an Asperon spray chamber. The Asperon is a nebulization system used in single-cell ICPMS analysis and specifically designed for the introduction of intact cells. It is a linear path spray chamber with an additional argon gas flow. This makeup flow is introduced through two inlets at the head of the chamber and avoids particles to collide with the walls of the chamber, contributing to improve the nebulization efficiency up to around 50%. This high performance is obtained by using very low sample flow rates, in the range of tens of microliters per minute, around 20 times lower than conventional nebulization systems. We are almost ready, however. For those who are not familiar with single particle ICPMS, just some keynotes. Well, single particle detection is performed in ICPMS by measuring in time-resolved mode using high data acquisition frequency, over 100 Hz. This is done by using dwell times below 10 milliseconds. Under such conditions, we get a continuous baseline here at the bottom. And when particles go into the plasma, we get short spikes due to the detection of the cloud of ions generated from each individual particle in the plasma. Thus, the first requirement is the use of these short dwell times. First, instruments working in single particle detection were limited to use dwell times in the range of milliseconds. 3 to 10 milliseconds were typically used. However, with the last generations of instruments, shorter dwell times in the range of microseconds are available. This can be as low as 10 microseconds, although dwell times from 200 to 100 microseconds are typically used. The second requirement is that particle suspensions must be sufficiently diluted. The reason is that each spike must be produced by one single particle. Although maximum number concentration depends on the dwell time selected and the flux of particles in the plasma, in general terms we are talking about suspensions below 10 to the 9 particles per liter. Because the duration of the clouds of ions is below 1 millisecond, if we choose dwell times in the range of 3 to 10 milliseconds, we are going to get pulses, which are one-reading events. However, when we use dwell times in the range of microseconds, we get peaks consisting of several readings. In this case, the intensity of the particle event is the sum of the intensity of the readings along the peak, which is equal to the intensity of the pulse. Now let's have a look to the baseline. The baseline is due to the background of the mass we are measuring, but it can also be due to the presence of dissolved form of the element we are monitoring. Because particle concentration is very low, just some of the droplets in the aerosol will contain a particle, but all the droplets will contain the dissolved element, of course, if it is present in the sample. This means that for suspension of common nanoparticles, the baseline is going to be very close to zero, whereas if this contains ionic gold, higher intensities will be expected. This is going to be our situation when measuring carbon. Carbon baselines are going to be significant in our single particle analysis because of the ubiquitous presence of non-particulate forms of carbon in the plasma that come from the argon but also from air and water. In any case, from this time scan, we can get different types of analytical information. First, the number of particle events is proportional to the number concentration of particles in the suspension. Second, the intensity of the events is proportional to the mass of element in each particle detected. Finally, from the baseline intensity, we can get information about the concentration of dissolved species of the element that we are measuring. I would like to draw your attention to the information that we can get from the intensity of a particle event. We must bear in mind that single particle ICPMS just provides direct information about the mass of element in a particle. Strictly speaking, we are detecting particles that contain such element, carbon for instance. However, we are talking about the size of specific types of particles most of the time. To convert this mass of element in the particle into the size of the particle, we need additional information that is not provided by the ICPMS. We need to know the shape of the particle, its composition, and its density. But now let's go back to the nebulization. When using the Esperon system, there are two flow rates to bear in mind, the nebulization and the makeup flow rates. This is an advantage because with the nebulizer flow rate, we just control the nebulization process. On the other hand, the makeup flow rate contributes to control the residence time of the particles in the plasma through the total argon gas flow rate, that is the sum of the nebulizer and the makeup flow rates. Here, we can see a study of both flow rates by measuring a suspension of polystyrene microparticles of 2.2 micrometers. We can see similar behaviors with all these flow rates for the number of particle events, plotted here in the left, and the intensity of the events, plotted in the right. The number of particle events depends on the nebulization efficiency of the particles, whereas the intensity of the events reveals the efficiency of the volatilization and atomization of the particles, as well as of the ionization of the atoms. That we already know that is not very high for carbon. What we can see here is that we can get optimal conditions for all these processes for different makeup flow rates just by selecting the appropriate nebulization flow rate, as long as the total argon flow rate is 1.2 liters per minute. In our case, we selected an optimal nebulizer flow rate of 1 liter per minute and a makeup flow rate of 0.2 liters per minute. Under such conditions, we got similar nebulization efficiencies for gold nanoparticles than for polystyrene microparticles of 2.2 micrometers. However, the efficiency was much smaller for larger microparticles of around 5 micrometers. This means that with the Aspern introduction system, microplastics up to 2-3 micrometers nebulize like nanoparticles and dissolve species. For this reason, the procedures and standard used in single particle ICPMS for the determination of the nebulization efficiency with particles could also be used here for microparticles. We have seen that large microparticles over 3 micrometers were not nebulized with the same efficiency of the smaller ones. In spite of this limitation, we can see here a linear behavior when we plot the particle intensity with respect to the cube of the particle diameter. The bias of the measured diameters with respect to the certified ones were below 10% in all cases. This behavior confirms that microplastics up to 5 micrometers were volatilized, atomized, and ionized with the same efficiency. This is not strange because plastics have low molecular masses and boiling points, much lower than most inorganic nanoparticles. This means that even larger plastic microparticles may have similar behavior. What about the smaller microparticles? This is a matter of size detection limits. Basically, when we measure by single particle ICPMS, the objective is to detect particle event that must be high enough over the noise of the baseline. If we consider that the particles are solid spheres with a diameter d, we can calculate the size limit of detection by using this expression as the cubic root of a multiple of the standard deviation of the baseline divided by the slope of a calibration of the peak height versus the cube diameter. Although you can find different criteria for estimation of size detection limits in the literature, we have demonstrated that 5 sigma criterion is a safe option to avoid the occurrence of false positives arising from the baseline readings. It is the criterion we have followed here. You will have noticed that I have shown a particle event recorded as a peak. This means that we are working with dwell times in the microsecond range. Let's explain why. Well, bear in mind that all the measurements are done in counts. When using microsecond instead of millisecond dwell times, the baseline intensity becomes smaller and hence is a standard deviation, which may improve size detection limits. However, as we can see here on the left, for gold nanoparticles, the height of the peaks becomes smaller as we use shorter dwell times, degrading size limits of detection. In the end, I'm focusing on size detection limits. Long microsecond dwell times are recommended to get low size detection limits once the peak can be correctly identified. In our case, microparticle events had a mean width of around 800 microseconds, and using a dwell time of 200 microseconds, up to 4 or 5 readings per peak were obtained. Under such conditions, the size limit of detection was 1.2 micrometers for polystyrene microspheres. Time-resolved signals recorded as time scans must be further processed to obtain size as well as size distribution information. Basically, for the individual particle events, the particle event intensity histogram can be plotted and transformed into the corresponding particle size distribution. We need to consider the nebulization efficiency, the sample flow rate, and the mass concentration calibration with dissolved carbon. I'm not going in details about this calculation because they can be performed by using the syngistic nano application in a similar way than for nanoparticles. In this regard, the size distributions that we have got for plastic microparticles are wider than the original ones, as we can see here in the third figure. The PCR standard of latex microparticles of 2.2 micrometers is highly monodispersed, with narrow size distribution of 1%. We can see here in black. However, when this standard was measured by single particle ICPMS, distributions around 10 times broader were obtained, although this did not affect to the mean diameters measured. This broadening was probably due to the different trajectories of plastic microparticles through the plasma. Once we have talked about the size determination of plastic microparticles, it's time to talk about the number concentration of the suspensions. As I have explained before, single particle detection is based on the fact that detected spikes must correspond to individual particles and not to two or more particles. It is a matter of Poisson statistics that during the duration of a particle event, other particle gets the plasma and both were recorded in a single spike. This probability increased with number concentration, and under the conditions of this work, it was significant over 2 times 10 to the 9 particles per liter, limiting the linear range of number concentration calibrations. The lower end of this calibration depends on the attainable limits of detection. Because of the restrictive 5 sigma criterion selected for identification of particle events, remember that we wanted to avoid the occurrence of false positives, blanks show no events. Under such conditions, the limit of detection for a counting process like this corresponds to the detection of 3 particles, which can be related to the number concentration by considering the nebulization efficiency, the sample flow rate, and the total acquisition time. This means that number concentration detection limits of 5 times 10 to the 5 particles per liter can be achieved by measuring during 1 minute, and 5 times less if the acquisition time is increased to 5 minutes. Well, now that we know the performance of single particle ICPMS for the detection of microplastics, it's time to analyze samples. This is a summary of the conditions selected for detecting microplastics by single particle ICPMS. We used an Nexion 2000 instrument equipped with an Asperon nebulization system and the Syngistics nano application. The plasma conditions were those used routinely. The RF power was 1600 watts, the plasma gas flow rate 15 liters per minute, the auxiliary gas flow rate 1.2 liters per minute, the nebulizer gas flow rate 1 liter per minute, and the additional makeup gas was 0.2 liters per minute in the Asperon spray chamber. We used the isotope 13 of carbon. We didn't use the isotope 12 because of the higher background of this mass, as we have seen at the beginning of the webinar. In such case, the detector should have been used in analog mode, losing the performance of the ion counting mode required in single particle detection. To reduce size detection limits as much as possible, we use a dwell time of 200 microseconds. Finally, the sample flow rate was 16 microliters per minute and the total acquisition time of 1 minute, although it had to be increased up to 5 minutes to record a representative number of particles events in some cases. Our first application consists in the detection of microplastics in cosmetics. Microplastics are intentionally added to cosmetics and personal care products mainly as abrasive agents for skin exfoliation and teeth cleaning, ending up in domestic sewers once they have been used, and after that in urban sewage networks, wastewater treatment plants, and eventually in rivers and sea. The US passed a Microbit-Free Water Act in 2015, banning cosmetics that contain intentionally added plastic microbits from 2018. In the European Union, the European Chemical Agency has been working since 2018 in a restriction of intentionally added microplastics, which is expected to be passed this year. The sample preparation for the analysis of cosmetics was quite simple. 0.5 grams of the sample were diluted in 250 milliliters of ultra-pure water and sonicated for 15 minutes. The samples consisted of exfoliating hair conditioners and face cleansers purchased in local supermarkets and web pages. Because microbits used in cosmetics can be quite large, a filtration step through 10 micrometers filters was included to avoid clogging of the nebulizers. Blanks free of spikes were obtained. whereas all the samples analyzed showed a significant number of them. As I have said, no particle events were detected in the ultra-pure water blank, whereas the number of spikes in the procedure blank was very low, with an average of 3 events. The events detected in the samples allow to estimate particle concentrations from 10 to the 7 up to 10 to the 11 particles per gram, depending on the sample. On the other hand, the morphology of the particles was studied by optical microscopy, showing irregular shapes in most cases. Just sample PCP1 showed rounded shapes. To know the composition of the microplastics, they were analyzed by FTIR after their isolation by centrifugation in methanol. The analysis confirmed that microplastics were made of polyethylene, although microplastics in product PCP3 could not be isolated because it was insoluble in methanol. This information about morphology and composition is especially relevant for estimating the size of the particles detected. The size of the particles was calculated as an equivalent diameter, assuming that the particles were spherical and their composition polyethylene, with a carbon mass fraction of 0.856 and a density of 0.95 grams per cubic centimeter. Whereas in the first application we studied the presence of intentionally added microparticles, in the second example we studied non-intentionally added microplastics. They were particles released from tea bags made of plastic polymers during the process of brewing. First, the plastic tea bags were opened with steel scissors to remove the leaves. Next, the empty bags were thoroughly washed with ultra-pure water and air-dried. Next, 2 empty bags were put in a glass vial filled with 10 milliliters of ultra-pure water, heated to 100 degrees Celsius, and left to brew for 5 minutes. After that, the bags were removed and the liquid directly analyzed by single-particle ICPMS after cooling it to room temperature. As in the previous case, we got blanks free of spikes, whereas the measurements showed clearly that microplastics had been released from the tea bags. On average, 1 particle event was detected in ultra-pure water and procedural blanks. The number of events detected in the samples were lower than in the previous case, and acquisition times had to be increased up to 5 minutes. Under such conditions, we could estimate the release of around 10 to the 4 particles per tea bag, with mean sizes around 2 micrometers. As in the previous case, the shape of the particles was very irregular, as we can see here in the images obtained by scanning electron microscopy. The composition of the plastic tea bags determined by FTIR was polylactic acid for tea bags A and B, and PET for tea bag C. Hence, the size of the particles was calculated again as an equivalent diameter, assuming that the particles were spherical and considering the carbon mass fraction and the density of the corresponding polymer. The take-home message of the webinar can be summarized in the following points. Single-particle ICPMS has proven to be a feasible technique for the detection of microplastics by monitoring carbon-13. Under the conditions of the developed method, the minimum sizes detected were limited to around 1 micrometer. The concentration detection limits achieved were in the range of hundreds of particles per milliliter. Finally, bearing in mind that single-particle ICPMS detects particles containing carbon, single-particle ICPMS is suitable as a screen method for the rapid detection of microplastics, although it must be complemented with other techniques to confirm the nature of the detected particles. You can find more detailed information in the application note recently released by PerkinElmer, Unlocking Carbon-13 with Single-Particle ICPMS, Feasibility Study for Microplastic Detection, and our publication in Talanta, Analysis of Microplastics in Consumer Products by Single-Particle Inductively Coupled Plasma Mass Spectrometry using the carbon-13 isotope. Thank you very much for your time, and now I am happy to answer your questions.
Thank you so much. What a wonderful presentation. We're going to get started with our Q&A. Feel free to continue to ask questions in the question section. And thank you to those who have already participated by asking questions. So our first question is going to be, will this work with a PFA nebulizer and spray chamber? Also, will I be able to detect graphite?
Excuse me, could you repeat the question, because I...
Of course. Will this work with a PFA nebulizer and spray chamber? And there's a second part to the question, but we can address that after.
Sorry, I'm sorry, but I'm hearing quite well here.
Okay. Will this work with a PFA nebulizer and spray chamber?
Yeah, well, we are using the point we're working with a PFA nebulizer. At this point for us is has not been a problem, because we have got quite good blanks. Then well, the emission from a PFA nebulizer, I think at this with the sensitivity we are achieving with our system, is not a serious problem, because well, the number concentration detection limit is around we are getting 100 particles per liter. That is low, but I think is not low enough to get to get a blank or spikes from this plasticware.
Okay, great, thank you. The next question is, the method presented allows the detection of microplastics in the range of several micrometers. What about larger and smaller microplastics?
Well, the point with the method that we have seen is that well, it has some clear limitation. Of course, we are getting let's say quantitative results in the range of 1-3 micrometers. In this range, we are getting really quantitative results, both in number concentration and also in size. Of course, in a real sample, we are going to find a kind of continuum size, a broader range of particles, of the particle size. But the point with the method is that what is important from our point of view is that this method must be considered a screening method. The point is that by using this method, we can know that we have microparticles of course, in the range of 1-3, but well, at least we know that we have these microparticles, and then we can move to another technique. The key point here is the screening capability of the method.
Great, thank you. The next question is regarding carbon background. The carbon background in the blank samples were incredibly low. Did you do any removal of dissolved carbon?
Well, in the samples, well, in some cases the background was quite good, well, quite low, and but in other cases it was not so low. For instance, some of the cosmetics had to be analyzed undiluted, and there was some dissolved carbon background. And in those cases, well, it was not so low. But in general terms, most of the you must bear in mind that in some of the cosmetics there was some a large dilution, and in the release study we were working just with the plastic tea bags and the ultra pure water. In that cases, well, the typical backgrounds intensities were around 10 counts. But if For instance, working with other kind of samples with with a higher carbon dissolved carbon levels, background levels are going to be higher. But in this case, we didn't do we don't remove carbon in any way.
Okay, great. And then the next question is, have you tried doing this in surface water samples? And if not, do you think it could work? Or would the interference of bacterial cells and algae be problematic?
Well, with respect to waters, the problem with natural waters, for instance, could be that well, these levels, for instance, of organic carbon, or more, I think probably most important in fresh waters, these carbonates. But in that case, they could be removed just by acidification and purging. And there was a second part. Sorry.
I was just wondering if there would be interference from algae and bacteria in surface water.
Okay. Well, no. Well, we have checked. We have checked it, and yes, you can think on a bacteria like a carbon-containing bioparticle. But well, in fact, there is no the content of carbon in a single bacteria is low enough not to be detected, because we have to bear in mind that what we are detecting is the mass of carbon per particle. Then in practice, we have checked this and with bacteria suspension, and well, just in case there is big lumps or bacteria, you can get some spike. But in a similar way, well, this can be removed. This can be removed, yes, by digesting the sample with a bit of with some nitric acid and some heating. You can digest these bioparticles.
Okay, great. Thank you. And then we have someone wondering if you could share some thoughts and experience in field flow fractionation ICPMS collaboration.
Well, my experience, our experience with FFF ICPMS is that, well, I would say that it's not an easy technique, because I think the problem is not the hyphenation, but is to handle properly AF4, because, well, there is a lot of things to bear in mind and to control. And, well, I think it is important to the experience of the people optimizing the programs. On the other hand, well, you can get interesting information, and in the end, you can complement the information. For instance, if you you can get information from single particle ICPMS, mostly related to the particles, but and also to the dissolved fraction of one element. If you couple with FFF, you can get the detailed information about this dissolved fraction. For instance, suppose that there's an element that is complex by organic matter, for instance, and then you can get this kind of information. Then there is they complement we can say that they complement each other, but from the technical point of view, I think it's easier to handle single particle ICPMS than FF4 ICPMS.
Okay, great. Thank you. Next question is, are the equations involved for nanoparticle analysis valid for microparticles, or is it necessary to make adoptions and consensus? So again, are the equations involved for nanoparticle analysis valid for microparticles?
Well, the big difference or the problem with microparticles is that we have to be able to introduce with a high efficiency in the plasma. Then this is the reason why we have exchanged the conventional nebulization system for the Asperon system, because the Asperon system has been designed specifically for the introduction of particles, well, in fact, for cells, but we can think on these cells as particles in the micrometer range. That I think it is the big difference. You can use a conventional sample introduction system, but we are going to get lower fluxes of nanoparticles and in the end lower sensitivity from the point of view of the number of particles. Then in the end you'll have to work with higher or more concentrated samples. Yeah.
Great, thank you. The next question is, what is the advantage of single particle ICPMS over FE-ICM imaging, which might be more informative? So what are the advantages of single particle ICPMS?
Sorry, in comparison with?
With FE-ICM imaging.
Sorry, I didn't got this. Well, the difference with imaging techniques, I would say that we can get quantitative information in really quantitative information. With respect to the number concentration that we are not going to get with these imaging techniques. And secondly, I think this is the speed. Normally, single particle ICPMS is we can say that this is a rapid technique. In 1 minute, you can get information, and you can get information about not just about size, but also about number concentration. Even is not the case with carbon, because we are not interested here in the dissolved fraction in a sample, but also about something that you can see, that is the dissolved fraction, the ionic. For instance, if you are measuring silver, you get information about this dissolved silver. That is not possible with an imaging technique.
Okay, thank you. Next question is about the main difficulty in determining microplastics and ICPMS. The question states, do you believe that the main difficulty in determining microplastics is the high background for samples containing high carbon concentration?
Yeah, of course. This is one of the, well, we have been talking about, let's say, the standard limitations, but of course, the sample matrix with a high carbon content is going to affect the size detection limits, but in these cases, the only solution is to implement. We need to implement some kind of previous treatment. I've been talking. Suppose that the typical example could be, this is I already mentioned. This is a natural water with a high carbonate content, for instance. Of course, I think the easiest way is to some acidification of the sample and some purging, and we are removing the carbonate as CO2, and And well, in this case, it works correctly. But in other cases, we have to try to remove this carbon background.
Okay, great. Thank you. The next question is, could any other sample introduction systems be used?
Well, I already mentioned. Yeah, the point with other sample introduction system is what I commented before. The Asperon the Asperon system has been designed for this introduction of microparticles, and if we are going to work with a conventional one, well, in the end, we are going to lose this sensitivity with respect to the number concentration, the low number concentration that we have achieved. Then that is, I think, is the point. Of course, I am sure that we have to bear in mind that this is one of the first method about this, and I'm pretty sure that in the near future people will start to think about this, and probably will have new solutions for all these current problems we have now.
Okay, thank you. And then, do you think that with larger particles, the residence time in plasma would be long enough for the particles to get volatilized? And if so, what would the upper size be? So I can ask that again. Do you think that with larger particles, the residence time in the plasma would be long enough for the particles to get volatilized?
Well, yes. Well, with plastics, I think so, because well, I think that all the processes in the plasma we need enough time, enough residence time. Then we have bear in mind that well, we have optimized this all this work, all this method for 2-3 micrometers. We have seen that from up to 5 micrometers, everything is okay. All the particles volatilize and ionize with the same efficiency. We didn't check larger microparticles because of the clogging problems. Try to avoid these clogging problems, and because of, we have seen that nebulization efficiency was lower. But I think there will be there is no problem with this volatilization of larger particles, because well. The key points are the molecular mass and the boiling point. Then, and this is for a plastic, it's not a problem. For another inorganic particle, it could be. For instance, if we introduce silica particles larger than around 1 micrometers, we are these particles larger than 1 micrometer are not volatilized correctly. But with carbon, it's much easier, let's say.
Okay, great. And we will answer one more question. Why don't we see nano in size of 10 micrometers? Might go along with what you just answered.
If I understand, if I have any problem with working with 10 nanometers, sorry,
Yeah, so why did you not work with any 10 micrometers sizes? I think is what the question is asking.
But over probably it's my fault because I'm not following the question or are not getting the question correctly. What was the problem with this higher than micrometers?
Yes. Would there be a problem with working with
Yeah,
size?
Sorry. In our case, we avoid this large particles because of clogging mainly. Because normally the nebulizers, the capillary of the inner capillary of the nebulizer is around 100, 150 micrometers, and doing some experiments from time to time, we had problems with these larger particles. Then there's some problem of clogging. Then there was the reason because a part of the nebulization efficiency of these larger particles is lower, but we avoid these large diameters. We have to bear in mind that, for instance, a cell is a soft particle, but in this case, these are rigid particles. Then the nebulizers can be clogged.
Okay, great. Thank you. And I did say that was the last question, but we just got a few more. So thank you again for everyone participating. Next question is, were there any 3 to 5 micrometer plastics that accumulated in the capillary tubing?
No, we have not noticed any trouble about this. Yeah, no, it has not been a problem for us.
Okay, thank you. And then which nebulizer did you use with the spray chamber, with the Aspiron spray chamber?
Well, in the paper we have published, we have been used a prototype. Prototype. This is a flow focusing prototype developed by a Spanish company. But at the beginning we were working with a standard microconcentric nebulizer without any problem except those that I was talking at the beginning. At the beginning, we started working with quite large particles. We had some problems, and then we moved to this other nebulizer because of the wider inner diameter. But I can say that the behavior and the performance is. I would say that this is almost the same, the microconcentric nebulizer and this flow focusing nebulizer.
Thank you. And then the final question, which reference material is used to calculate nebulization efficiency?
Well, standards reference material for plastics, I would say that it's not, at least for us, it has not been easy to find, thinking on number concentrations. And we have used this BCR reference material that is certified for size, but also it include the number concentration. Then, but it's not certified, but I think it has been, at least we have the recommended value. But what we saw was that by using these gold nanoparticles, the point is that we are getting the same as these 2 micrometers polystyrene particles behave in the same way that the gold let's say nanoparticles, gold nanoparticle, for instance. We can use both particles as a standard for determination of the nebulization efficiency. Then, because basically we did this determination by the frequency method. by using the number concentration of both suspensions.
Okay, great. And that concludes the final question. Thank you so much for everyone that participated in the Q&A. And thank you, Francisco, for an excellent presentation and Q&A session. The recording of this presentation will be available within the next 48 hours, so please keep your eyes open for an email. Thank you, everyone, for attending. I hope you enjoyed.
You are welcome.
Thank you. Bye. Everyone have a nice rest of your day. Thank you.